Okay, we've been speaking about equations of motion and driving those equation of motions as well. Today, we'll go ahead and describe the categories of motion and where to use what technique. So we'll be comparing situation of motion or the type of motion with the type of calculations or type of solution that we can apply to it. Now, motion in general can be described as moving with a uniform speed. Just 1 second. I think somebody needs a. Okay, I'm back. Motion can be classified into two types: moving with uniform speed or moving with non-uniform speed. When an object is moving with non-uniform speed, there are further two possibilities. It can be moving with a uniform change in speed, and it can be moving with a variable change in speed. Excuse me. What we mean by that is a uniform speed can be with a actually a non-uniform speed can be with a uniform acceleration, and it can be with non-uniform acceleration. Now, if an object is moving with uniform speed, it becomes very easy. You can find distance with speed multiplied by time, or you can find average speed with total distance divided by time. So these formulas become handy if an object is moving with uniform speed. So these formulas are that you can use in case of average velocity or constant velocity. If an object is moving with a uniform acceleration, in that case, all equations of motion become handy. If you remember, in the last lesson, we were discussing about uh, equation of motion where we proved them. If you remember, we discussed this thing that only if acceleration is constant, average velocity is initial velocity plus final velocity divided by 2. And I gave you an example of numbers that if numbers are changing with the uniform difference, the average of first and last is the average of all the numbers. You don't need to add all the numbers and then divide with the number of numbers. Instead, what you can do is you just add first and last number, add it, the sum is divided by 2, and that will give you average. But this only applies if the difference is uniform. And all these equations that we did in the previous class, okay, all these equations, they have one condition in common, that they only apply to a case where the object is moving with constant speed, no, sorry, constant acceleration. Now, uniform acceleration, if in case of uniform acceleration, we can use equations of motion. Okay, this title is given to three formulas. V, final velocity equals to initial velocity plus acceleration into time, 2as equals to v square minus u square, as equals to ut plus 1 over 2 at square. So these three are considered as equation of motion. First one is first equation, second one is second equation, and third one is third equation. Do you need to remember the order? Answer is no. That is not one of the requirements. But this is how this thing is. Another formula other than this equation of motion is S equals to 1 over 2 initial velocity plus final velocity. Only this expression gives you average velocity. Multiply by time. That is another formula for finding distance. And one more is Vt minus 1 over 2 At square. Okay, now if you see how many different variables are used in all of these equations, the answer is 5. And what are those variables? U is initial speed or velocity. V is final speed or velocity. S is distance traveled, or in some cases, it can be velocity. Okay, actually, velocity, so my bad, correction. Distance traveled can also be displacement. Velocity and displacement, they can be special cases of speed and distance, respectively. For example, if we have distance in a specific direction, it becomes displacement. And similarly, speed in a certain direction becomes velocity. So for the cases where the object is moving in a single direction on a straight path, velocity and speed are the same thing. Distance and displacement are also the same thing if object is moving in one single direction. Now, T is time taken, and is acceleration. Now, if you further focus on all of the formulas that are written on the right side of the screen right now, you will find out one similarity in all of the equations, that every single equation is using only 4 variables at the same time. Look at the first one. This equation is missing one of the 5 variables. If you focus, you will find that S is missing. Now, this gives you a clue which equation to be used in a certain specific condition. How? Pay attention. If there is a situation where displacement is not given or distance traveled is not given, and neither it is required to be calculated, so it means that you have to deal with a situation where neither distance is given nor we need to find it, what formula we can use. Like in that case, VUAT will be related in some situation. One of these 4 variables is missing, and we can use this formula to find that variable. Similarly, if you focus on the next question, there is one of the variable missing. Which one is that? It is T, time. So it means this equation can help us if neither we have time, but we still have to find one of the variables without using time. This is the equation that we should use. Then, if we do not have final velocity, this one. If we do not have any information about acceleration, nor it is involved or needed to be calculated, we can use this one. And if initial velocity is missing, we can use this one. So all these equations are suitable for specific situation. Now, and what is the common condition for all of them? You cannot apply these equations unless it is given that the acceleration is constant. You assume that acceleration is constant. Otherwise, there is no way you can use any of these equations. Now, Let me put one more condition on the same thing. What if acceleration is constant and object starts from rest? If an object starts from rest and acceleration is constant, that means u equal to 0. This can be put as a special case. If u equal to 0, all above formulas can be customized. See how. Number one, the first equation, v equals to at, will now become v equals to u plus at, where u is 0, will become v equals to
80.
at. Good. Now, the second equation, if u is 0, it will become v square equals to 2as, because u is 0. Third equation, if u is 0, it will become s equals to, because if u is 0, u multiply by t, the whole factor will become 0.
Half 80 square.
Great. It is half a t square. And this can be reorganized or rearranged as a equals to 2s over t square and t equals to 2s over a square root. So all these formulas can be found from this one. Like actually, it is the same formula in different arrangement. Now, last one is s equals to half v into t. It was actually u plus v into t. If u is 0, it is just simply half vt. So all these equations, they are coming with more conditions on them. Let me box all the important formulas. So all these formulas, they have one condition. And the condition is, look, actually two conditions. Number one is that the acceleration is constant. Number two is initial velocity is constant as well. So none of these formulas can be applied if an object is not moving with constant acceleration or it does not have initial speed equals to 0. Let me put a big, because these are not ordinary formulas. They need special conditions for their application. Now, what if we are dealing with non-uniform acceleration? In that case, we seek help from calculus. Derivative of distance with respect to time gives you speed. Derivative of speed with respect to time gives you instantaneous acceleration. Integral of acceleration, actually derivative of speed with respect to time gives you acceleration. That is done. Now, integral of acceleration with respect to time gives you change of speed, and integral of speed with respect to time gives you change of displacement. But luckily, all this is not included in our syllabus, not in our syllabus. And by syllabus, I mean 9702 physics. Yes. So we will not be using any of them. But you, if you're studying math as well, will be studying these formulas in mechanics. Now, what you'll be studying here about non-uniform acceleration. Estimate gradient by plotting tangent to curve path, curve part of graph and selecting 2 points on it. Estimate area under speed time graph to calculate distance traveled. What I mean by this is sometimes you can be offered a situation with you're not dealing with a straight line graph and the examiner asks you to estimate the gradient. So why is he's not asking you to calculate? Because he is a rational person. He knows that this is not in your syllabus. You don't know, like if you're just physics student, you're not math student, you're not familiar with derivatives and things like that. So if you're dealing with a curve like this, and examiner wants you to know or calculate acceleration at this point, how will you do it? Because it is a curve graph. How can you find acceleration in this case? Now, what you need to do is, first of all, you need to draw a tangent. So what you do is, you draw a line that only touches the graph at one point and be specific, not only any one point, at the point the examiner wants you to calculate acceleration or the gradient of. So once you do that, now what you have to do is, you have to complete a triangle. Draw a vertical line from here, draw a horizontal line from there. You will end up with a right angle triangle like this. Okay. Now this will be the rise, and this is run. If you are more comfortable with y2 minus y1 over x2 minus x1, be my guest. You can use that formula as well. So now, what if examiner wants you to calculate area under this thing? In that case, there are multiple ways you can do it. You can split the whole thing into small parts like this. Okay, it depends on how accurate you want to be. The smaller the gap is, more accurate the answer will be. But if you split it into something like this, then you can find areas of like in the first one is an example of, if you see here, this is an example of a triangle. Then you have a trapezium, another trapezium, another trapezium on the side. So you can find all these shapes, area of all these shapes separately, and then you can add them to find total area under the graph. So that is one technique. One more is that you can, or one more technique is that you can split it into a single regular shape. For example, like this. So what you do is you take some of the area from outside and you ignore some of the area from inside, and you make a judgment over there. This is just totally like decision made by your eye, that you have to estimate that this area that you're taking from the outside, this is the area that is not under the graph, but you're adding it. That is a plus error. And this is the area that you're subtracting, that you're ignoring. That is area under the graph, but you are not considering it. So that is a negative error. And this is self compensatory errors help you to estimate area under the graph. Now you can find area under this blue line. That will not be an accurate answer, but that will be very close to the correct answer. Okay, if anyone does not understand that, you can interrupt. The red line is a curved line, and a task was to calculate area under the graph. What does this phrase actually mean? The red line is the graph, and this is the x-axis, which is in this case the time axis. And if you're looking for the area in between, like I hope you can see this red curve, and area between this red curve and the time axis, this area is called area under the graph. Now, what I did is, because I have no formula for this kind of shape, it is some of you might think that it is a quarter of a circle, but it is not. It is not. It is not a quarter of a circle. It looks like one, but it's not. Uh, Secondly, I have to calculate area, and I have no formula for this shape. So what I do is I draw a straight line, making a judgment with my eye that I will take some of the area out and I will add some of the area from the outside. This is just a judgment. This will be like, if somebody expert will do it, he will get an answer which will be in 0.01 range of actual answer. But even if you do it with like in third or fourth attempt, you will find out that you are getting pretty close to the correct answer. So in this case, what I did is I added some area from the outside. I'm considering it as positive error, and I'm minusing or subtracting or ignoring some of the area that is between the graph and the time axis, and I'm considering it as negative error. This positive and negative error, they self-compensate with one another, and I get approximately a very good estimate of area under the graph. Now, mm, when this is done, it is time for doing a very simple, very easy question. Let's see. The question is a bullet of mass uh, 28 gram is fired with a speed of 180 meter per second into a soft log of wood. The bullet stops after penetrating 6.0 centimeter into wood. A. Calculate acceleration of bullet in the log. B. Actually, no, it is A 1 and A2 is calculate how long bullet kept moving in the log. Like, what was the time for which the bullet was traveling? For the time for which the bullet was in motion, we have to calculate that time. And the B part is describe or enlist list any assumption if you made one. So it is a 2-mark question, another 2-mark question, and a 1-mark question. Okay. You can take a screenshot and you you have to solve this question. Let me put some of the information that can help you. Yeah. Okay, you can take screenshot now and solve this question. And you have exactly 5 minutes for that. And once you're done, you take picture of your work, send it in the private window or in the group. It's totally up to you. I will pause the recording here.